Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of medical imaging course. Since there are students who have not earlier done any image processing related courses like computer vision or image and video processing, in this class what we will do is let's have some basic introduction to digital images. So for those who have already done some course, this could serve as a review class. One common question that comes to the mind is when can an object be imaged? So there are two important aspects here. One is you should have a sensor that is capable of detecting the energy of the electromagnetic wave, or for that matter any other signal that has an interaction with the object and got affected by the profile of the object. Say for example, if we are using visible light for the sake of getting an image of the object, so in that case we should have a sensor that detects the intensity of the visible light. The second aspect is the wavelength of the electromagnetic wave should be compatible to see your object of interest. More specifically, if you look at the wavelengths of the electromagnetic wave compared to the object of interest, the wavelength should be of a similar size or smaller, so that it can pass through the object and you could be able to get the profiling of the object. Well, there could be other scenarios also. This is a general statement about when you can see an object. This illustration we have seen earlier also on how we get a digital image of an object. Without loss of generality, we will discuss by using the visible light as the source, and you could later generalize and extend it to various other signals that you are going to use for capturing the digital image of the object. So you have an object here and the source of light falls on it, and there is an imaging system, and this imaging system has sensors that can sense the intensity of the light falling over a specific area. That area is governed by the size of the array of sensors you have, and then you digitize the resulting values in order to get the digital image version of that. Now let's take a look at what exactly it means by digitizing the output of these sensors. Assume that again, the moment we are drawing something and showing you digitally, it is no more a continuous one, but for the sake of understanding, let's consider that what you have here is having a continuous profile. So now let's take one line here and let's draw the intensity profile here. This is in order to understand what it means by digitization of an image. So you could see here there are two aspects. One is the spatial resolution. At what points do you would like to store the values of the intensities? So that's the spatial discretization is one thing that you are going to do. Another thing is at these points, as you could see in the first row second image there, that the values could vary very finely. So for example, if you exactly measure the value, for example take it as 2.456783 and so on, depending on to what precision you are going to measure it, to what tolerance value you are going to measure it. But that's not how we would be storing the values. So we would be doing, if you call it as an intensity, you would be doing intensity quantization as well here for storing its values. So there is this quantization. With those quantizations, this is how you get the values. Since there is a discretization done on the spatial domain as well in the x along that x along the line that you have taken also, you store the values at particular points. So the moment you are creating a digital image, two important phenomena would happen. One is discretization in the spatial domain and quantization of the intensity values that you are going to store. So sampling and quantization. Anyway, this is true for any signal, 1D signal, 2D signal or 3D signal in general. This is nothing new that we are discussing, but now we are just discussing it in the context of image processing. Well, the moment you are discretizing in the spatial domain, you would get the whole within that. Let's say take this part, you could see here within that, if you consider the continuous version of intensities here for this block, that will have a variation, but you could think of it as you are integrating the whole intensities there and representing it by a single finite value with limited number of digits or precision. So that's why within that each element you have one single intensity value assigned to it. The same thing we are talking about here, spatial and gray level resolution. Another way of saying it is you are discretizing spatially or you are sampling spatially. So that is what dictates the spatial resolution that you would be getting here, and gray level resolution is the quantization you are doing there in terms of the intensity values. Then the very fundamental and important question is what is the rate at which I could take samples spatially, so that still I would get a meaningful and a representative image of a physical scene. Assuming that your signal has limited frequency spectrum, or in other words, your signal being a band limited signal, then the Nyquist sampling theorem would tell you what rate you need to take samples along the x direction and along the y direction, assuming that your image is a 2D image. Anyway, frequency domain analysis of images will come little later after few more classes. For now, after this class, we would first start looking into the spatial domain image enhancements. Another question is, how do you represent an image? One way that you could think of it as, now once you had sampled the image in both x and y, so now you have rows and columns. At each of those grid points, now you have certain intensity values, and then also remember that we already quantized these values, so you have a specific set of possible values that each of these grid points can take. So one way you could think of representing an image is like a surface. So you have x, y in 2D, okay, and your third dimension being the intensity values at those intersecting grid points. Well, we will be doing all this processing in a 2D plane. If you are going to have a visualization of it, this is probably not a very convenient one. So what you would be doing, in fact, most of the times, is that you assign in intensity values starting from, let's say, the least intensity being black, highest intensity being white, and intermediately you will have the gray levels, and that's how you would be representing the values instead of showing it as a surface. So in fact you have a 3D data, but this is how you show the image as 2D, or in other words in a 2D plane. Of course you could think of other representations also, like for example you could see here the outside rectangular part is having 0 value. Assume that this is somewhere in between 155 or 100, whatever. This is something at the highest value 255, okay, or many times this need not be 0 to 255. Assume that the least intensity is 0, highest is 1, and somewhere in between means it could go from, so any value in between 0 to 1. So assume now this is 0 outside, middle is 0.5, and inside one here the D is the shape D is having 1. So another way is, this is how you could represent. Hope that representation is clear to you. If you want to give a mathematical form to it, x and y representing you the indices along the horizontal axis, and vertical axis. Okay, which are the rows and which are columns, what is exactly x and y. The notation could vary from tool to tool, but in general, if you look at it, image is a function of x and y. Along the row the index is x, and along the column the index is y, and the value which you are getting there is the intensity value. That's how you could mathematically represent the image. So the same image, depending on the programming language you are going to use, the index could either start from 0 or it could start from 1. If I remember correctly, in MATLAB, the index for images starts from 1, whereas in C and C++, we start the index values from 0. But anyway, the size, you typically mention it in terms of size, m rows and n columns, let's say here. So if you are starting your index from 0, you will go till m minus 1. Similarly, column, if you are starting from 0, if there are n columns, you will go from 0 to n minus 1. So this is as far as the sampling in x and y directions is concerned. Another thing we have discussed is how do you quantize the intensity values. To do that, one way you quantify this quantization is using a variable. Let's say how many bits are you going to use for representing these intensity values. Assume that you are using a single bit to represent intensity values. Then the next question would be how many different values or distinct values can you represent while you are using a single bit for storing the intensity values. So that being a binary bit, they can take either 0 and 1. So in that case, you could represent, if you are taking a single bit and assuming that these are all unsigned numbers, that means you do not use any of the digit for storing the sign information and all values are positive, in other words. So in that case, if you are using a single bit, you can store two distinct intensity values. Suppose if you are using 2 bits, okay, then 0 0 0 1 1 0 1 1. So with 2 bits you could store 4 distinct values. You could continue this further and you will see that if you are using k bits for storing the intensity values, you can in fact represent 2 power k distinct intensity values. So depending on that, you could make a quantization of the intensity values and accordingly store it. And now, ignoring for the time being about the compression of these lossy or lossless compression of this data, if you are simply looking at number of bits required for storing an image of size m rows and n columns, that would be m by n by k, where m is number of rows into number of columns. So at so many locations you need to store the intensity values, and at each location you are storing the intensity value using k bits. So total number of bits required is m multiplied by n multiplied by k, and with this representation, as we just now discussed, you could store up to 2 power k distinct values whenever you are using k bits for storing the intensity values. Assume for the time being that number of rows is equal to number of columns, and assume that here the first column is showing you the number of rows and columns that you have in an image. So it says the image size, for example, for the first row is 32 by 32, so 32 rows and 32 columns. Now if you are using a single bit, as we discussed just now, it could store two distinct values, so that L, number of distinct values, is 2, and so the number of bits required for storing these values is 32 by 32. That's, in other words, 2 power 5 multiplied by 2 power 5, that is 2 power 10. 2 power 10 is 1024. So 1024 bits are required if you are using a single bit to store an image of size 32 by 32. In other words, that's what we refer to as 1 kilobit, right? Suppose if you are using 2, this gets multiplied by 2. If you are using 3, this gets multiplied by 3. So this way, if I tell you what are the number of rows and columns of an image and how many bits am I going to use for storing intensity values at each location of this grid, then you will be able to tell me, in case where no compression is used, how many bits are required for storing that image. This is another visualization that is going to illustrate us on importance of these bits. Say for example, let's start from here, from the down. So this image for example is the case where you are simply using 1 bit for intensity values. Okay, forget about number of rows and columns, which is same for all the images. If you are just using 2 values, sometimes we refer to it as mask, where background is having 1 value and foreground is having another value. Let's say in this case 1 bit means you either 0 or 1. In computer vision, for 2D images you would be using 8 bits to store the values. So what would be the range of values that you could get there? It would be from 0 to 2 power 8 minus 1. So you would get values from 0 to 255. So this is how you could see here. You can observe here one important fact, that you should be using sufficient number of bits to store the intensity values, so that you have a clear distinction between the surrounding pixel values. Okay, pixel, since I'm sure you already know this word, I am using it, we'll come back to it very soon. So to have distinct pixel surrounding pixel values, so that's the effect of quantization of intensities. This is a repetition of what we have already seen. This is how we look at an image. As we could see here, you see a different structures and all, but the moment you are treating it as a digital image and processing in a computer, all it's going to look at is an array of numbers. So we will see as we move on in this course how to make a sense of these numbers and how to make an interpretation of these numbers or process these numbers the way we would be doing a processing as a human. At least to the extent possible, we would like to reach to the best possible level there. If you would like to have a more formal definition for a digital image, as we already discussed, there are two phenomena that are happening. One is sampling in the spatial domain and quantization in terms of the intensity values that will be stored. So a far more formal definition is a digital image is defined by integrating and sampling continuous data in a spatial domain. So in that particular region, let's say the region could in practice can correspond to the size of the array. So you would be integrating the whole value that comes there. So that's why integrating and sampling continuous data in a spatial domain. The word we use here for representing this whole area or unit area is pixel. This terminology has been introduced in late 1960s and is introduced by a group of scientists at JPL in California. Another way of representation is what you see here on the right hand side. So you could think each one as a vertex of a graph, okay, and it's connected. The connectedness, the edges representing that what is it that you consider as neighbors to it, right, and the value of that vertex representing the intensity value that you are assigning to it. As you have already seen in the earlier videos, that while representing the 3D, it's not just one 2D image you have a sequence of images. Now if here it is representing an area here, a 2D plane integrated over a particular area of the sensor, in that case whatever you have in 3D, it is not referred to as pixel, but rather it is referred to as voxel, meaning volume element. That's what it refers to. Whatever we discussed so far with a 2D array, those images we refer to them as grayscale images, but you could in fact have color images as well. One common way of representing the color images is same way m rows and n columns are there, and at each of the pixels, instead of having a single intensity value like what we did with the grayscale images, you could have in fact 3 values there. So You could think of them as if three images, three grayscale images as well. So one representing the red channel intensity value, another the value in the green channel, and the last one being the blue channel. Again, the distinction need not always be red, green, blue. There are other ways of representation. Sometimes they are more efficient and they are more distinctive and more useful while representing the images. One of such representation is hue, brightness and saturation. Anyway, I will not go right now into the details of RGB to hue, saturation, brightness conversion back and forth, but just it's good enough to know at this point that this is also there. And in case of medical images also, sometimes we use color images, but maybe not in this course. Actually, you would come across this particularly in diffusion MR imaging and also in tractography, where you would like to keep track of the orientation or the path of these connections from different parts of the different oxals of this brain. It is good enough for you to know at this point that even in medical images you could have a color image representation, but the purpose is slightly different than what you would see in computer vision. This is being one example being diffusion MR imaging. Let me make few more points here. In case of computer vision, where most of the images are 2D, there it is very common that you would be using 8 bits for representing the images. On the other hand, when it comes to medical images, you would usually use more number of bits than 8. You could use, for example, 16 bits is not at all uncommon, particularly if you are using CT images, and even in MR images you could use up to 16 bits, or 32 bits is also quite common. Suppose if you are using 16 bits, that means now you could have values of intensities starting from 0 to 2 power 16 minus 1. So the moment you are loading a medical image and trying to interpret it, you need to make sure what is the data type that is used for storing the image. That plays a very important role, unlike in other areas like computer vision. Last point that I would like to mention in this video is, usually in case of computer vision, we don't explicitly keep track of what is the distance between two pixels. On the contrary, this is a very important information in medical imaging, because this distance will be usually different, or in other words, the sampling rate is different in X, Y and Z. This is quite common. If you are capturing the CT image of the head, you might take a slice here, and depending on the purpose and the application, the rate at which you take the Z slices would differ. Most of your image processing tasks you would be performing in the spatial domain rather than in the voxel domain. So before you do any image processing tasks, it is important for you to transform from the voxel domain to the spatial domain, and there the distances in X, Y, Z with which you have sampled being different, you have to explicitly keep track of it and accordingly move to the spatial domain. Of course, at the end of your application, again you may come back to the voxel domain, but this is an important point to keep it in mind. So with that, we will wrap up this video lecture, and in the next video lecture, let's take a look at image enhancements in the spatial domain. Okay, thanks for watching. See you in the next video lecture. Bye. Take care.